Okay. All right, so hopefully everyone's back and can hear me again. Hopefully that's all set. And also hopefully that explanation for number 13 is what you wanted. So chapter 11 quiz number 7. Why are A and C not, wait, did I read that right? Number 7? Yeah. Why are A and C not equal? Oh yeah, that's, there's some macabre geometry going on there. So let's get that set up. Sorry. All right. So the entirely legitimate question is why are A and C not equal? Um, so we're okay with the idea that D and B are both equal and 0. I hope we're okay with that idea because the line of action for D points through the center and the line of action for B points through the center. So the torque of D is 0 and the torque of B is 0. But it looks like you should be able to say, well, let's look at, say, A, and we say, well, A, that's the line of action. So this is the moment arm for A. And then we say, well, what if we had C? Well, this is the line of action for C, and that's the moment arm for C. And it looks to your eye right away that this is not, that those are equal because they're both sort of some distance. But it comes back to a hexagon that's divided this way is really 6 equilateral triangles. Get my program to work out nicely for us. All right, so we have an equilateral triangle, and the side for A, this is definitely the moment arm for A, right? Because we've got this triangle. On the other hand, this is the moment arm for C. It's the altitude of the triangle. And that is clearly shorter because if the leg, right, first of all, I guess let's emphasize that it is this triangle we're talking about now. And then going a little bit more afield, but the thing we want is the leg in a right triangle, and the leg of a right triangle is always less than the hypotenuse. Right, so yeah, that was a little tricky. That was a little nasty geometry, and it took me a little bit, and I taught geometry for a couple of years, so that was a little embarrassing. I want to stress out anything with the torques actually sketching out the line of action and drawing the moment arm seems to really activate things in the brain. Number 17 from chapter 10, sure. All right, so this is chapter 10, number 17. Discus thrower starts from rest and begins to rotate constant angle acceleration of whatever. How many revolutions does a viscous thrower angular speed need to reach 6.3 rad per second, and how much time does it take? So this is horrible flashback to chapter 2 type stuff. It's probably worthwhile to start looking at like what are we given and what does it tell us. So we start from rest, and that's going to tell us that omega initial is 0. And then we rotate with a constant angular acceleration. Someone else just came in, so welcome. And this tells us that alpha is 2.2 rad per second square. And then we end up wrapping up with an angular speed. We wrap up with an angular speed of 6.3. So that's going to be omega final. And then what are we being asked for? So we're being asked for how many revolutions. Revolutions is answered by an angle. So this is asking for a theta final. And then later on, they're asking us for how much time. And that's going to be t. All right, so that's sort of our setup. So in part A, we are not given time, right? A neither have nor want t. So we're going to go through our equation sheets. I'm going to say of the kinematic equations, were there any things without t? And of course, there's one such equation, which is that the final velocity squared is the initial velocity squared plus twice times the acceleration times the change in position. Now, we did that in chapter 2 as vf squared is v0 or vi squared, is what it's size, plus 2a delta x, and this is now the rotational equivalent of it. So I'm going to go down here and I'm going to say something like 6.3 radians per second quantity squared is 0 radians per second quantity squared plus twice that acceleration times delta theta. And if we solve for that, we'll get 6.3 squared over 2 times 2.2. And we get delta theta is 9.02. But remember that these equations all assume that they're in radians. And just to make life, annoying, the textbook asks for revolutions, not radians. So we're going to have to convert that by saying, well, there's 1 revolution for every 2 pi radians. Let's see. So this over 2 over pi, it's about 1.4 revolutions. So I'm not sure. I'm not sure where your 3 comes from. It looks like it might be a factor of 2 lurking here that one of us might have made a mistake on. But they wanted an answer in revolutions, so you should definitely have answered in revolutions. But and revolutions is a measure of an angle, so it's okay in general to end it with a delta theta that's in revolutions. But the equations we derived basically want everything to be in radians. And at the very least, you do have to note that we have radians here, so somebody's going to have to be converted. Just for completeness, we didn't do part B, so let's just do that quickly, but that's actually relatively easy. For part B, we can come back to that the definition of an acceleration is that it's the change in speed over the change in time. So for us, it's going to be 6.2 radians per second minus 0 radians per second over delta t, but we were given that this was 2.2 radians per second square. And so all told, we end up with delta t is 6.2 radians per second. Oh, 6.2? Sorry, 6.3 radians per second over 2.2 radians per second square. The radians go away nicely. The seconds become just seconds, and we get 6.3 over 2.2 is just about 2.86 seconds. It's actually okay. Some people who solved it did B first and used that to get theta, and that's okay. So hopefully that had everything that you wanted on that. Yes, I can definitely wait half a minute and go back to the other screen. Right. Which is fine, although do remember that, again, this entire video thing is going to be uploaded as soon as it finishes converting, which takes maybe about 10 minutes once we're done. Although you might want to rewrite it because my writing is pretty badly. All right, so this is the other screen. Also, I want to point out or make clear, I've now uploaded video solutions for all of the textbook problems. So if you're looking over any of those, you can certainly use that as a resource too. My hope is that probably not tomorrow, but on Saturday, I'm going to try and crank out solutions for all of the sample problems, the typer type problems, the ones that are more like this, not this, that are more like this. I have some of those done, but I don't have all of them done. But that's going to be my plan for Saturday. Have we done 53 in class together? That's a good question. I think we did, but we can certainly take a look at it again. Yeah, we talked about this one quickly in class, although we didn't actually get the numbers. But the numbers are actually not that hard. Okay. The basic thing is it really just comes down to two formulas. The kinetic energy is a half I omega square. And we have, let's see, we have the M and R, so we can get I. And we have omega, although it's in RPM, so just convert to revs. And then part B is just that the power is the work over delta T, and the work is K over T in this case. Sorry, pretty sad. Just the energy you just found over delta T. So you can solve for delta T. I guess for completeness, the I here is just going to be mr squared. All right. So anything else jump out at you? Oh, there we go. If we have time, we definitely do. Let's see. Oh, okay. I think I know which one you're talking about. I'll have to find it, but I think let's see. We're looking at. Uh, I think we're looking at this one. B5CT21 is what you said. Yep. So this is samples chapter 9, number 7, and it talks about two boxes on a frictionless surface. Yada yada yada. But the question that Laney brings up is grappling with how the momentum is conserved, but not the energy. So there's actually sort of a useful thing in physics that it's worth sort of keeping in mind, which is that there's a hierarchy to what things tend to be conserved. And it turns out that angular momentum um, is conserved most easily, most often. And then linear momentum is sort of the next that you check. And then finally, energy. So even though we do energy first and it's relatively natural, as a conservation principle, it's limited because only certain forces have it. So the general thing is you should sort of assume it's not unless there's a good reason to think that it is. Um, in this case, what's going on is that while the total energy probably would be conserved, since the only things acting are this is the spring, and the spring force is conservative. So on some level, you're like, well, why isn't energy conserved? And it is if we had any information about the spring. In other words, if we knew something about this spring, we could compute. If we knew the distance it was stretched and it's k, if we knew k and we knew s, then we would be able to figure out the potential energy. Right? We'd be able to say that the potential energy is a half k s squared, and then it would turn out that that would equal the kinetic energy the thing picks up. So it's a little, we're being a little facetious here. The total energy is conserved in this problem, but it is unknown because we don't know enough about the spring. So that turns out to be true but useless. On the other hand, the momentum is definitely also conserved because, which is totally independent of energy conservation. And I guess I really do want to stress they are totally separate from each other. There's never a connection between momentum conservation and energy conservation. For momentum conservation, the key thing is that linear momentum is conserved if all forces are internal. In other words, if the only thing causing a change in motion of some object is some other thing inside the system. So looking at this problem, the guy on the left is accelerated by the spring, and the guy on the right is accelerated by the spring, and they push back on the spring, but all of those are internal. So the total momentum of the system is going to be conserved. And since nothing was moving at the start, the total momentum of the system is going to be 0. So total momentum is 0, but the total momentum is the guy on the left plus the guy on the right. And I want to be a little careful here, so I'm going to put him as minus to indicate the fact that he's moving that way. So that has to be 0, which tells us that the two momenta have to be equal. Right? They have to be equal in size, but opposite in direction. Once you know that the total, once you know that the size and the momentum are going to be equal, then it's pretty easy to see that the faster guy, the heavier guy has to move slower because for each of them, P is mv. So if this is a constant number and this has gotten larger, then that must get smaller. No problem. That was a little roundabout, but I think it covered the important stuff. I do want to kind of really stress there's a student pothole people fall into because energy conservation is kind of cool and we tell you it's the most important thing and it really is, but it is kind of limited. You have to know all the forces, and we don't know the spring force here because we don't know the spring constant. All right, we're good for about another 7 minutes. So. So if we knew the spring constant, actually, we'd actually have to be careful setting up this problem, because if we knew the spring constant and the compression of the spring, we'd have overspecified the problem. Whereas there really is only going to be, well, no, I take that back. So what you could do, this is not a thing. This is going to be beyond what we'd expect. But if you knew both the spring constant and the initial stretch in the spring, then that gives you the potential energy in the spring. And then after release, the kinetic energy would have to equal that potential energy. So you'd be able to do something like saying like 1/2 m1 times the speed of 1 squared plus 1/2 m2 times the speed of 2 squared is equal to 1/2 the spring constant times the separation squared. And you also know that m1 times minus v1 plus m2 times v2 is 0, because this is energy conservation. And this is momentum conservation. So at this point, you could actually solve for v1 and v2 and get actual numbers out. So knowing the spring constant would tell you the velocities, but this is algebraically, this would be not fun to do algebraically. There are tricks that would make it moderately less painful, but they're not interesting. Basically, once you know that the energy is conserved and you have values for it, then these one-dimensional collision type problems become completely determined. Physicists say you lose your degree of freedom, and once you know the inbounds, you have to know the outbound. Well, so I want to be a little careful because I think I spoke a little too quickly. In this one, the energy is conserved, but we don't know it. So that's a true thing, but not useful. And we're sort of a ruthlessly pragmatic science. So because things that are true but not useful in problem solving, we don't end up using here. If that helps for your question. And I'm happy to talk about Katie's, but she hasn't actually asked anything in about 10 minutes. So if you have something, Katie, make sure that you also chime in to make sure everybody gets the attention they need. Let's see, I don't know if I have a problem for this. So Katie said, I don't know if you have a problem for this, but is there something we can do for an object where slipping is present? That's a good point, because I don't think we have a problem offhand on it. We did talk a little bit in class about it. I'm trying to think if it's a sort of thing. Well, sure. I mean, we could do. Sure, we could do something which actually wouldn't be a bad problem. So let's say we have a wheel rolling across the floor. Sorry, my input device is going a little weird. There we go. So let's say we have a wheel, pretend it's touching the floor, and it is well, an easy way to start off is we can say, let's assume that we know its radius and its mass. Make up some good numbers for that. And then it is moving forward with some velocity, let's say 2.1 meters per second, and it is rotating at, I just want to get something not quite right, so let's just say 3 radians. No, let's say 2 radians per second. All right, so the first thing would be, is it slipping? That's our first kind of question. That's maybe A. And part B might be if mu kinetic is 0.2, what are A and alpha? And realistically, although it's a little beyond what you would see on a test, this could really be saying, find the time until it stops slipping. So I'm going to talk about that, but that's probably a little bit beyond what I would ask on a test. But how would we know if it's slipping? So we know that to be not slipping, right, for no slipping, we need V equals R omega. So we can say for us, R omega is 0.65 meters times 2 radians per second, which is 1.3 meters per second. So we know that it is in fact slipping. So yes, it is slipping. Right? This is not equal to 2.1. So yes, it slips. So I'm going to go unknown. Let's see, maybe we can copy the screen. Some stuff. All right, and now let's clean this up. So now our next question is, what's actually happening? So we want to figure out which way the wheel and such is moving. If it is slipping, but it's not, that means that since we know that V is more than omega, then the point, our circle a little bit. So we have V is greater than R omega, which means the point is being dragged forward more than it's being carried back by the rotation. So the actual point is slipping forward, right? The point of contact slips forward. But in that case, if the actual point of contact is slipping forward, then friction must be resisting that. So the force of friction points that way. And that's going to be really important because it will do two things. It will create an acceleration that way, which is opposed to the velocity and therefore will be slowing, right? So A is opposite to V, so the wheel gets slower. But also, it's going to be exerting a torque, right? And that torque is counterclockwise. Oh, sorry, it's clockwise. So it's going to produce an acceleration like that. And that means A alpha is aligned with omega. So wheel spins faster. And we could find both of these things by saying that, you know, the frictional force equals the mass times the acceleration, which means that mu times the normal force equals the mass times the acceleration, but the normal force is just mg. And so everything turns out that A is just mu times g, which happens a lot actually for things that slide. And then the next thing to do is that the torque, which is F times the radius, equals I alpha. So mu mg times r equals mr squared times alpha. And so I can also find out what alpha is going to be. It's going to be mu g over r. It's hard for me to imagine I'd actually ask you to compute things, but I think I could. I think it's entirely reasonable to say, given a wheel with this kind of velocity, which way does friction point? And what is the torque? What is friction going to do to the velocity, and what is it going to do to the spin? But the general argument is if your velocity is more than r omega, then friction will slow down the wheel, but make it slower. Okay. And if velocity is less than r omega, then the friction will spin, will speed up the wheel, the center, but spin down the wheel. So yep. So to summarize sort of these things, there are sort of two possible cases. If the velocity is greater than r omega, then it's moving too quickly, right, for the wheel. So friction will slow the wheel, but increase its spin. Right, it'll make the wheel go slower, but spin faster. And then the flip side is if the velocity is less than r omega, then it will speed the wheel, but decrease the spin. And honestly, the way to remember this, I guess what I'll say here is that if v equals r omega, then no changes because friction equals 0. But actually, the easiest way to think is that friction always does whatever it needs to do to make them equal. So in this case, since v, in the first case, where v is too low, it must raise v and lower r omega so that they get closer to being equal. And in this case, where v is too high, then it must lower v but raise r omega because it's always driving them towards equal. So we're getting a warning. I'm getting a warning that they're gonna drop me out in about a minute. So I think we're more or less done. If there's something I didn't address, then please definitely send me an email, and I will do a quick video thing sometime tomorrow and send it back. But if not, the video for this will be posted probably within, let's say, half an hour. I don't know how long it takes to convert the video. And then remember that there will be something Sunday afternoon. I think it was at 4 o'clock, but it's definitely on Blackblog. Anyway, I hope this was helpful to you, and I hope your classmates who were not able to make it find the video helpful. And if not, I guess that's sort of their loss. So I will see you guys on Monday. But I do want to remind you, anytime if there's something over the weekend, definitely feel free to send an email, and I will do my best to respond and get something out to everyone. Have a good night, everyone.